Okay, let's start. So, yeah. Okay, how's it going, everyone? The name of my paper, as you all know by now, was "Hey, my malware knows physics: attacking PLCs with physical model-aware rootkits." All right, so as a high-level overview, it was a 2017 paper, so it's relevant, applicable, and pretty much up-to-date, and it was a collaboration between Rutgers University and Florida International University. And basically the question that they were trying to answer is whether you're able to implement a stealthy attack on PLC systems whereby you're not going after the HMI, or the human-machine interface, and we'll explain that as we go on. And they essentially created HARVEY, which is a reference to Harvey Two-Face, who's a villain in the Batman cinematic universe. And the analogy applies really well because it's essentially the idea of the operator seeing the benign, non-harmful side of Harvey, whereas underneath it's the deformed attack, or the other side of Harvey. And they implemented this on a power grid control system, as we will see later on. So just in terms of the overview of ICSs, or industrial control systems, they're essentially made up of a hierarchy of 3 levels, as you can see there. The upper level, the management level, contains the SCADA, which stands for Supervised Control and Data Acquisition Unit. Below that, you have your control level, which contains your PLC and an HMI, which we'll be looking into in this paper. And then below that's a field level, which basically contains all the entities and units that interact with the physical world. So then zooming in on how Harvey was implemented, it was essentially this information transfer from the HMI, or human machine interface, to the PLCs. It's sending information back and forth there. And then the PLC controls to the actuators and sensors. So now, last time we went over Stuxnet, and just to give a view of what it did, it compromised both the PLC and the human-machine interface, whereby it was able to send malicious code or malicious controls to the actuators from the PLC, but also it took over the human-machine interface because without doing that, the operators would have been able to see that the attack was happening. And so in the Stuxnet case, they played back a pre-recorded readings in order to try and fool the operators. In terms of the Harvey attack, they didn't want to deal with the HMI, as we'll go into a bit later, but they wanted to focus the attack solely on the PLC, whereby they had to know what the physical model of the system was in order to be able to first maliciously attack it, and secondly, spoof the readings to the HMI. Looking at a PLC more closely, it's essentially the interface between the physical world and the virtual world, and that's broken down into these 3 kind of hierarchical layers: your control layer, where the control logic actually happens, your firmware, and your hardware. And the authors of the paper dubbed this attack the man in the PLC attack, whereby they focused solely on the firmware. So just quickly, the scope and assumptions, I feel it's applicable to note these now. As I said, they wanted to mount a stealthy attack on PLC systems, and particularly stealthy because those have been shown in the past to be far more effective than simply shutting the system down in order for them to reboot thereafter. They were concerned only with PLC attacks, not looking to the human-machine interface, because they didn't want to have to deal with the hurdles of having to get through those security implementations thereof. They also weren't too focused on how the malware was injected into the PLCs. They do mention a couple of ways that this could be done, and I'll mention those a bit later on. However, that wasn't the main focus. The main focus was a system that knows the physical model and is able to use that to its advantage. And that's a segue into the assumption that the physical model of the system is known, which is an important assumption and pivotal to the success of this attack. So what is a rootkit? I took this definition, which I thought encapsulated it quite well. A rootkit is a clandestine computer program designed to provide continued privileged access to a computer whilst actively hiding its presence. And the actively hiding is essential to this, and it's one of the key features of the HARVEY Rootkit. So what exactly does it do, or how does it work, whatnot. It's invisible to the ICS world. Again, that's the industrial control systems world, where it's undetectable to the human operators, so they cannot see any anomalies from the readings that they're getting. It's undetectable also from a software point of view, and in particular these intrusion detection devices. It's also transparent to the control layer, which is important because otherwise the control layer would try and counteract the effects by sending new commands and whatnot. So this ensures that the operators, from the operator's point of view, the system remains consistent with expectations in order to keep it stealthy. And then it uses the model, which again they assume is known, firstly in order to spoof the values back to the HMI, and secondly to essentially inverse the control function or the loss function of the system in order to have an optimal adversarial objective function. And in terms of the infection method that I mentioned, there were 3 of them that they briefly touched on but didn't go into a whole lot of detail about. And those were firmware upgrades, which they said was the primary way that they suggested that this attack could happen, as well as local attacks through SD card or JTAG, which is the one that they particularly looked at in terms of this attack, as well as runtime attacks, so code injections such as with SQL attacks and whatnot. Looking again at the PLC and just to show essentially under the hood how HARVEY is working, it essentially took the firmware and divided it into 2 layers, whereby from an operator's perspective you can only see a benign physical model, which is essentially this loop here, whereas under the hood or below this divide within the firmware you have this malicious model, which is sending adversarial optimal commands and taking the actual measurements in, while spoofing the fake, legitimate-looking measurements. So that was the theoretical part. In terms of physical implementation, I tested this on the Allen Bradley Compact Logics PLC, which is one of the largest vendors in the world, but as I mentioned, it's largely uncharted in terms of security research and investigation, and that runs the Cortex M3 ISA. In order to conduct the attack, they first had to reconstruct the firmware, and the way that they did this predominantly was through using JTAG in order to read the device memory. They had to read the base firmware off the PLC, which doesn't come as over the internet or whatever firmware upgrade. So they had to perform both online and offline analysis in order to fully decompose the firmware. Then they went through quite a lot of detail in terms of how they actually implemented the attack, and some of those milestones where they were able to identify the nested vector interrupt controller in order to disable the core functionality. And then because the PLCs are so, they're essentially GPIO units, which are taking in inputs and sending out outputs. And so they needed to determine the structure and the peripherals controlling those GPIOs. And once they're able to do that, they could take control of the LEDs on the outside of the module in order to spoof the readings and therefore keep this attack stealthy. And then because the system is so closely tied to with what the GPIOs were doing, once they'd done that, they were able to inject malicious code into an unused area within the system memory. And in the 2 subroutines that both take in data and send data out, they were able to change those, as I'll explain over there, in order to jump to their code. So this is the benign code where it would just run through, and they essentially take this and replace it with the malicious code where it's a branch to this location. And in this case, I wanted to spoof that an input was present where it actually was. So where this, it's quite hard to see, sorry about that, but where this should all be full Fs, they put a C at the end in order to make it seem like port 1 had an input. And then just in terms of the evaluation, I did want to mention one thing that stood out to me was just how large the PID attack code was in comparison to the actual code that's normally on the systems. And I see this personally as a potential flaw within the attack, in that if they were to look at the code size, they would be able to recognize just how much larger the code is. However, having said this, they did mention that there was a bunch of garbage code on the PLCs, which to me suggests that the operators of this aren't too concerned with the code size, and therefore it is plausible that this could go undetected. as well as just how much free memory there is again indicative of that. So then this was simulated in a real-world attack where they implemented it on a power system test bed. They did two scenarios essentially. One was a steady-state attack, which was kind of like a trivial test where they simply toggled a circuit breaker in order to see the effect of the system. That one didn't have too much success from an attack point of view. However, the second test, which was an adversarial optimal attack, they took the normal code or controller which runs, which is the optimal power flow, and they added this M to make it malicious. And in order to make it malicious, they did these three things, which was remove the safety conditions from the optimal power flow implementation. They reversed the cost optimization so instead of minimizing the cost, they maximize the cost. And then they implemented these stealth conditions, which I thought was also really clever, and they went in depth with regards to keeping this stealthy, in that they wanted to make sure that like the noises of the system remained consistent with how they should be. So they couldn't just fully shut down the system such that the operators could potentially detect it through side channels, essentially. And then just to show how essentially well their system did, none of us are really experts in the domain, but however, looking at these fake readings, we would assume that everything is nominal, especially given what the legitimate readings look like. You can clearly see there's a lot of difference between the two, and as I mentioned, those spikes do exceed the safety limits of the system, and given it enough time, that would be detrimental to the system. So for me, the main strength of the paper was they were able to show that a stealthy system could go undetected and do significant damage. Nothing particularly novel. But however, the weakness I felt was that they made a lot of presumptions and assumptions about the system in terms of getting the malicious code onto the system. And for me, the biggest one was knowing the model. They do mention that you could implement information gathering attacks in order to determine this. However, they don't go into it into a lot of depth, and so I think that's a potential flaw. However, as Prof has told us over and over and over again, if there's a possibility for something to happen, it is a flaw within the system and should be mitigated against, because you can't just assume, again, that the adversaries will not go to the lengths in order to get the information they need to mount a successful attack. So in conclusion, HARVEY is a physics-aware man-in-the PLC system capable of these stealthy attacks and is able to avoid detection through simulation of how the system should behave. And that's it.
Okay, great. So questions, comments? Anyone?
As you say, the model is they make assumption that they already know the model. So I know, the complex, usually in chemical process, the system identification is very hard, and usually in some companies, the model is modeling pretty hard. Even they, the people workers in the company, they don't know the perfect model. They just know the behavior of that model. So how could you fake that behavior?
Okay, so I thought that one way you could do this thing is imagine that initially their malware is in a learning mode. It has maintained the neural network, observes for a long while, input-output mapping, learns the model, and then automatically deploys it. Right? Remember, I mean, if the workers don't know the model, then actually it's to your advantage, because that means they don't expect, that they expect uncertainty. Anytime you have a noisy system, which essentially they are saying uncertain, then that gives the adversary a possibility of hiding under it. Right? So you could imagine that way. Now, having said that, yeah, I think assumptions about computing power of an adversary are easily justifiable, right? I mean, I was talking about crypto, I was doing that. So whenever you're talking about adversary, there are two things, at least two things, right? What is his compute power, and what does he know? And the problem with what does he know is that that's very hard to define, and that's what sort of we are saying.
Yeah, I was going to say also to go on with like the complexity of the model, I think just even relating to the next paper that's up is that this would be very easy to detect through almost any side channel, because if you're taking like a PLC that basically like performs some simple logic and just reads some data and then writes some values, and now you're simulating a whole system on it, like even just the PFD controller would take a lot more energy and maybe give off a lot of electromagnetic
So I think if the operator has a side channel to the plant, then of course this attack would be rapidly detected. Now having said that, remember in Stuxnet, it was too late, the damage was done, right? Because with these big plants and all, kind of the initial inclination is you are relying on your HMI. And if it's reporting things are okay, because all these systems are designed with then like notifications and some okay. So if it's not detected, then only when they actually are doing a physical inspection that they will detect it. So you do have a time window in which you can kind of cause damage and not be detected. So I think yes, all these are valid issues in the sense I cannot be in the attack mode, keep damaging for a long period of time because maybe when the machine is dying, it's making noise or stuff like that, and all, right? I mean, all those kind of things are there. But on the system identification part, you're right. It's hard, but actually because there is uncertainty, that also gives you some space to operate in that. Any other thoughts?
There is a part where they talk about forging the sensor values as opposed to like, I mean, there is a model that is existing and the observer at the HMI keeps seeing these values. He feeds in the control logic and he thinks that this should be coming, but these people have changed the control equations, but they don't talk much about how they actually, they don't justify it. I mean, they say that we have forged values in such a way, we have computed these values, and the observer keeps seeing what he should be seeing, but the damage is being done simultaneously. But there is a little bit of non-coherence between the two because they're not justified in terms of how actually the sensor values can be forged exactly.
Well, that goes back to the model part, right? I mean, if I have a model, then essentially I replace the physical plant by my model plant, and I'm getting control some actuation input, and I'm going to run through the model, and then I'm going to get some output, and that's what I'm going to repeat, right? I mean, so as long as my simulated model is good enough, we should be good to go. But that's a challenge problem. Actually, the other comment I would make is that in many attack scenarios, the adversary may have a similar plant. It could be another company which has a similar thing and is out to destroy its thing, or I don't know, at the level of countries messing with each other and all. I mean, it's not much to replicate a similar physical plant to learn about what the model might be and then kind of carry it. So all depends upon intent, resources, sort of thing. So I guess the way I would say is, apropos his last slide, in theory it is possible, in practice it will depend upon the monetary resources.
I think the last point, like they mentioned a lot of injection mechanisms, but then in the end they also said that a lot of it would not work because firmware cannot be easily updated. They have some sort of security for that, and the only way they could do it was through the data interface. So it's how likely, how safe?
How would they penetrate into the system? No, very good. Look, in a properly designed system, firstly, you could argue that malware shouldn't happen. Like on your Windows, Mac laptops, and in your smartphone, there are all these system integrity checks. So the firmware will not run if it is not appropriately signed, and so right there you have an issue. I guess the only thing is these are cheaply designed systems which lack a lot of those procedures and stuff like that. So that's probably the only comment. But I think as the concerns about these security issues cropping up, I'm sure these technologies migrate. I mean, and the things to make it happen later on in the course we talk about secure hardware on this and all, they have begun to emerge now in these lower end processors. So going forward, I guess the challenge is that a lot of these PLCs have like shelf life over they remain deployed for 30, 40 years. So stuff is going to be around for a while. Before moving on, next one, another a counterpart to this work which I also saw was the following. Do you guys know what is honeypot? Anyone heard this stuff?
Like you pretend that it's something and you lure it into that.
Lure it, exactly. So you pretend to be a target, okay, and the idea is you want to lure hackers so that you can trap them and then just attack. So physics aware honeypots. So the idea is you create a computer which looks to an adversary like it's a power plant. You attack it and you have simulated again into the model. You have like They'll attack it, they will think they're messing with a power plant or a transportation system or whatnot, but there is nothing real behind it. Okay, and this obviously works against remote hackers. I mean, if I'm bringing down lights in LA, then of course I'll know that my attack is succeeding. But a lot of these reports are, I mean, hackers and whatever, so Emission is not great. So physics aware hypothesis kind of complementary idea. I want to see them there. I don't think I've seen any paper on it yet, but
Like, they've said that, I mean, adding to the point that you mentioned, like they couldn't get through the firmware mechanism of like uploading malicious code to firmware so that they could directly update it to. I mean, is there no way to break that SHA-1? They said because a lot of these firmware
signed.
yeah, so signed. So in, I mean, like in with respect to Stuxnet, they had some like signatures by verified vendors. So is there anything similar that can be done to break those SHA-1 verifications?
SHA-1, I guess one of the other signatures, I don't know whether SHA-1, but some others were broken by the businesses from China. So some of these digital signatures you have to broken now.
Wasn't SHA-1 broken by like Google last year? Or they found like
Oh,
new solutions?
Yeah, I think there was one which was broken by Chinese, and then there was one by Google. Yeah, I don't know which one. I'll check it out then, because I'm going to cover digital signatures. So let's move on to the next presentation. So.
And this is actually from the same group.
All right. Hello, everyone. My name is Asita, and I'll be presenting the paper on contactless control flow monitoring via electromagnetic emanations. So the introductions for these two papers were very similar. So the idea is that ICSs are very important, and it's a really big market. And specifically for this paper, it's heavily focused on attacks directly onto the PLC. So the paper's main focus is on something that they call Zeus. And Zeus is essentially a control flow tracking solution. So what it is it's measuring the control flow of the PLC itself, which I'll define a little bit later. And the unique feature of this monitoring system is that it has no physical connection with the PLC device itself. So it's essentially just grabbing the electromagnetic signals that are coming from the PLC using a sensor, and it analyzes it using a neural network. And this paper talks about multiple tests that it ran, and it concluded for the specific PLCs that it ran on, it had an extremely high accuracy, which kind of shows how viable that this monitoring solution is. So actually one thing to notice on this setup, so you have the electromagnetic sensor pointed, it's very close to the PLC board. So obviously this PLC is taken apart and in a very experimental situation, and we have it collecting the waves and everything. So and if you notice, the sensor is actually very close to a specific chip, and here they have highlighted multiple points of emission. So when the PLC is actually running the code, there are multiple points. So for example, there's like the proprietary Allen Bradley chip. There's a few FPGA chips and SMD surface mount capacitors. So there are multiple sources that you can get these emissions from. And what they concluded was, I believe because it was also related to the surface area that it covers, they mainly focus on getting the electromagnetic signals from the Allen Bradley chip itself. So how does Zeus work? So as I mentioned before, Zeus is implementing a neural network. So it sits basically in between the human, the HMI and the PLC. And whenever the HMI uploads code to the PLC, it captures that logic. And what it does with that logic is it uses, it cuts it up and uses whatever combinations to determine the feasible control flows that this code, the PLC, how the PLC will use this code, and it trains a neural network. So this is actually done all offline between the Zeus monitoring system and the PLC. So what it will do is just like take the piece of code, exercise it, and measure the electromagnetic signals coming out, and from there it builds a network. So here's like a visual of how it works. So it takes, one important thing to notice here, which I'll talk about later, is that it takes the time domain training signal traces and converts them to spectrum sequences, which is actually in the frequency domain. And the reason they do that is because they found that the time domain is very noisy, and the frequency domain actually gets rid of a lot of that noise. And here they build a model, and in the deployment stage, the model is ready to use in real time, and it gets the query signals. And basically, it's able to determine whether there are some abnormalities in the control flow. And if there are, it'll alert the user. So coming into this, there's also a lot of assumptions that they have to make in terms of adversaries and what kind of capabilities this will have. So the usual way that there's a cause of failure is remote programming, things like code injection. And the reason this is because in the real world, there's a lot of security lags in security updates. It could take days or even months for PLCs to get the latest security patches and things like that. And another thing that they have to assume is that Zeus has a trusted path to the operators themselves, because the whole point of Zeus is to alert someone if there is an issue. So if there's no trusted path between Zeus and somebody who can do something about it, then it doesn't really serve its purpose fully. And the other thing is a network link. So the network link where the code is actually uploaded from the user to the PLC, that has to be trusted as well, because the Zeus will be using that code, and it's assuming that that code is what's being uploaded to the PLC. And another nice feature that it has is it actually works with binaries instead of source code. And this is really good from a configuration standpoint, because if there is no source code available, Zeus will still work. Another thing, which is, I would say, it's just out of scope, not really a limitation, but basically sensor channel attacks, like we talked about in the physics one, where the sensor data is forged. It has no way of telling that, because it's only monitoring the control flow of the PLC itself. So the big feature is the neural network. So it exercises all the feasible control flows, and it's very important that it eliminates all of the infeasible paths, because it doesn't want that in the network. Because if there's an infeasible path in the network, and that infeasible path ends up happening, then it'll think everything's all right, and that's definitely not good. And the other important thing about the neural network is they actually had two different networks that they trained. So they had the hidden Markov model, which is simply just a neural network, and they were able to train it on an Intel CPU. And the one that they actually ended up using is the LSTM model, which they had to train on a GPU, and that's a recurrent neural network. And you'll see later that the results show that the LSTM is much more accurate at classifying these signals. So a little more detail on what the electromagnetic signals actually are. So this paper actually goes to a very low level to explain how this works, which is actually really nice. So the electromagnetic signals are assumed to characterize the program execution, and at a very low level, the program is executing basic operators like add, XOR, and things like that. So here, this table shows that the network is able to identify these simple operators. So at a very low level, it works, and you can translate that up to higher levels. And what the electromagnetic signals are essentially just like changes of electric current inside the PLC itself. So in order to evaluate this model, what they did, so there's tables and there's also a bunch of graphs, but all of them basically show that the frequency LSTM network is the most accurate way to present it. So as you can see here, there are 10 different programs that they ran. And the reason they chose these 10 programs is because these ones provide enough variety with the basic operators that I showed in the previous slide. And so this table is in terms of accuracy, so how accurately it can predict the labels that it created for certain sequences. And in terms of performance, performance is related to time. So how fast can it determine the certain labels? And an interesting to note here is the sliding window sizes, because what it's doing is it's cutting up these signals into small windows. So they actually did some testing on what the optimal sliding window size is, and it turned out to be 200 microseconds. So if you make the sliding window too small, then that hurts the time it takes. So that hurts the performance. So I talked about a few of the positive things that this has. There's also a bunch of limitations. So this is not really a bad limitation, but they only tested it on Allen Bradley PLCs. But the thing is, the reason they chose Allen Bradley PLCs is because it owns the majority of the market. But even then, there's still PLCs that aren't Allen Bradley PLCs, so they will have to look into that. And also, if you guys notice in the first image of the setup, it's a very experimental setup. You have a sensor. So first of all, you have the PLC all opened up, which is not how it is in the real world. And you have the sensor really close. And it actually, if you look at that bottom graph, you can see that it's actually not getting any results when it's only 2 centimeters away from the PLC chip itself. So it has to be really close, and in a real-world situation, that's probably not possible. And the other thing is, since it's so experimental, potentially something like the PLC housing could affect the EM signals. The other thing I talked about was the multiple sources of emanation. So one of the good features of Zeus is that there's no configuration required on the user side because it is building its own network. So all you do is just put it there, and then it learns how the PLC works. But if there's the issue of having multiple sources and you have different PLCs, you don't know which source is the best. So that's definitely another issue that they need to look at. So in terms of related work, I would say vulnerability discovery and controller program analysis are relatively similar. So vulnerability discovery is basically, once you have had some sort of attack, one of the important features is that since you're using a network and all these different labeled patterns, you can actually or potentially determine when the injection actually happened, because you can notice where the control flow started varying, which is very useful because then you can expose vulnerabilities in the system. And the other thing is like alternatives, right? So instead of doing contactless, you could do power signal analysis. But the problem with power signal analysis is that you're actually physically connecting something to the PLC. And the problem with that is that you're drawing power from the PLC itself. So if you're drawing power from the PLC itself, you could potentially be affecting the real-time constraints or real-time performance that the PLC has. Whereas when you're doing contactless, you don't have any overhead at all. And also, this is very important in information security because patches take a long time to apply. So in conclusion, Zeus is a contactless way of analyzing the electromagnetic signals, and it uses its network to detect any abnormalities in control flow to alert the user. Through the sliding windows research, they saw that you can actually monitor these really high frequency processors with low frequency windows. And based on the test that they did only with Allen Bradley PLCs, it has a very high accuracy. And I would say probably the most important feature of Zeus is that the contactless monitoring the contactless monitoring results in zero overhead. Whereas something like power signal analysis or even putting it on the software stack adds a decent amount of overhead.
So what were the abnormalities they were testing against? Like, so the accuracy refers to the desired program that they were, right? But like, let's say a malware compromised some part of it. So
Yeah, well, so the idea is that when you have some sort of code injection, the control flow changes.
right.
So when the control flow changes, the EM signals are different.
Right.
So it's not able to classify it.
So were there any numbers on the discrimination there in the sense that so there were good numbers reporting when for a particular program running, right? But what about if I make a modification so that it's now an unknown program? How well is it able to discriminate that? Right? Isn't that the relevant?
So you're saying without training the network?
Right, because you don't have the luxury of training the network on a malware, right? So you've trained it on the desired program, and now the adversary has compromised the software, right? So now the execution path is no more what you had. So how well does it detect that normality?
Well, it should definitely detect it, because if it's adding malware to it, then the electromagnetic signals would be completely different. So it would just.
No, I mean the neural network may have just learned to say it's good, it's good, it's good all the time. So you'll get 100% accuracy on when you're testing on the good program, but you don't know what is it on the bad one. Let's say I want to create a system which discriminates between class A and class B, right? And class B is the abnormality, so it will appear one fine day.
Okay.
Most of the time it's class A, or let's say it's class A1, A2, A3, I trained on them, and class B occurs rarely, that's the malware class. I'll never train on that, right?
Yeah.
So if I can learn this thing very well, but if B occurs one fine on a one, how would I detect it? I've never trained on it.
No, so it's training on the signals that it knows.
Correct.
So that's like the pattern. So if B ran, that would be a different control flow, and it wouldn't be able to categorize.
Well, but it may mislead it against one of the existing ones, right? That's the part we don't know.
Yeah, that's true.
So what are they training on? Okay,
What are they? Okay, so
I didn't quite get the connection between that initial binary that is being transported, which I guess they have access to the binary.
yeah, so what happens is the HMI uploads the code to the PLC.
Right.
So it intercepts that code,
Right.
and so now it knows what codes, like all the code that will be running on the PLC. So what it does is offline, it trains it exercises all of that code, all the different combinations, all the possible feasible control flows on the PLC, and it records all the electromagnetic signals,
Right.
and that's a network. So that's
so the network is learning to say which control flow it, like which path it.
yeah.
goes
So
through,
it knows
right?
all of the
Possible-
patterns
all
that
the
are possible.
patterns, right?
So if you run something else,
Right.
chances are the
results
patterns will be different.
So the results are, so I guess those results I didn't understand, but presumably they are learning how to say, was it control flow, whatever, path 1 or path 2 or path 3,
Yeah.
right?
Sorry. Yeah. That table was about accuracy.
Okay.
Just
So they're learning how to say whether it's path 1 or path 2, path 2.
Yeah.
But what they are not learning is if it's, like, what is malware? Malware is some new path, right?
yeah. So it's something that wouldn't be in the label, part of any of the
Part
labels.
the-
So it will know. So it'll say, oh, this is like, I can't label this. So it's something else. So
Not
it's
obvious,
just,
not obvious, right? I mean,
Yeah.
in the sense that you have to inject the bad thing to say whether it identifies that, right? Did they do that? I guess what I'm saying is that, okay, let's imagine that all I had was one good path, okay? Then the neural network conceivably can just learn to always say it's good, it's good, it's good, so that when the malware comes, it never detects it.
okay.
Right? So accuracy is only part of the story, right? It has to also, you also have to have false, you have to, they have to show that they also detect bad
Yeah.
things with high accuracy, right? I don't know, did they do it?
I don't think they did. Yeah.
So, anyway, comments, thoughts, anyone?
There are a couple of other limitations that are also there. One thing to think upon is what if they use the same execution path but still give a different output? Your control flow need not have to actually change for a malware to occur always.
The value may differ.
Value can differ.
Yeah.
So that's one thing that this system cannot detect. And other thing is what if I just change the input and the output? Like the HARVEY paper. Here it checks only the control flow logic. What if I don't disturb the control flow logic?
But I add some additional.
So things like that can happen. And they don't talk about the noise rejection also. Like there'll be a lot of noise while taking up the sensor data with respect to the EM base. They don't tell how they actually take that sensor data and remove the noise to identify the signal.
I think they just
They changed the frequency.
frequency.
Oh, is it?
Yeah,
Okay.
frequency gets rid of a lot of the noise. Yeah.
The thing that I didn't understand is they said this would then get something like Stuxnet, but wasn't the binary already compromised when it was uploaded to the PLC with Stuxnet?
Yeah.
It is HMI.
The binary was compromised at the HMI.
Yeah, they say that in the paper that it would protect against something like Stuxnet. But
Yeah, I guess, I mean, I think the usage model is a bit muddled, but, so I think a couple of years ago, DARPA, which is a big DoD research agency, they started a program which is kind of in the space. So their motivation was the following, that organizations deploy all these IoT devices, which are obviously from kind of various vendors, sometimes they're open source, sometimes they're closed source, but you cannot really put instrumentation, software instrumentation in the software itself to detect malware because a couple of things. Firstly, most of these things are single address space, so your checking code cannot really run reliably. When malware has compromised this thing, will probably compromise your checking code also. Another thing is a lot of times very hard to kind of apply. So they were looking for a solution where can we monitor our network of IoT devices for attacks by, okay. And there are kind of two cases that the program kind of seeking to address. One is known source code, or whatever, known binary code, because when they do the binary code, they're pretty good decomposition tools. So essentially, once you have binary, you can always go back to a reasonable looking source code. There are open source decomposition tools. So known code versus unknown code, right? I mean, those are the two cases. Unknown code is obviously harder. And what this program from DARPA, the challenge they basically threw was that through non-invasive means, namely by monitoring emissions of various types, so current and EMI and whatnot, light, sound, stuff like that. So do you make an inference about whether something has gone wrong? Okay, and the work in part was motivated by some work leading up to this, where a group at Georgia Tech kind of showed that they could identify instructions in a Intel processor. So those, there has also been work where people have shown for certain kind of processors you can even make a distinction between data values. So like multiplication by 0 is different than multiplication of its non-zero values. Okay, so they may have different signatures. So those were the goals. I think it's still an incredibly hard problem, but as to how close the sensor needs to be or cannot, if we are the good guys, so you can imagine that designing an IoT device where you put these kind of sensors as part of your packaging as a way to sense the health status of the IoT device, right? Because you realize that there is no way you can put your instrumentation in software because the software is easily compromisable. So you kind of surround your hardware, so EMI or power or I don't know what other side channels can you think of when people heat is another one. So they all offer different cost trade-offs, but EMI is actually a relatively easy one. I mean, these sensors are not that expensive, and if you are far from the chip, then you get what is called as a far field signature, electromagnetics, driven electromagnetics. And if you're right next to it, you can potentially identify right, like really what's happening locally in that area of the chip, and you can really kind of make some interesting distinction. So it's not that outlandish to imagine that you deliberately design this kind of non-invasive sensing in IoTs. So, okay, yeah.
In the Stuxnet case, though, surely they would have been trained without the malicious code running. Therefore, when the malicious code did run, it would have been able to be picked up.
So, in case of Stuxnet, if Iranians had developed a classifier for good signature versus anything else, binary classifier, then they would have been able to detect. They probably would have also been able to detect if they were to put some sort of thing in the middle of the HMI and the PLC, which looked at the code and verified something, right? Those are possibilities. So I think what could have, whatever the attacker, I guess, is trying to Americans, what could they have done? Well, if there is a check happening after the HMI, then it's very hard for them to overcome without compromising this thing because the entry point in case of Stuxnet was the HMI. Everything else kind of lives on that, right? So Iranians could have created kind of a solid firewall between them, and I bet you all kind of all the places which are worried about this kind of thing, they probably are, right? In the sense that I think there is a man in the middle defense, probably that firewall of some sort, probably between existing things. I think the newer PLCs, I wonder whether they are beginning to adopt code signing and these kind of things to address such type issues. I mean, our smartphones do it. There's no reason that PLCs can't. I mean, technologically, it's not that you don't know how to protect software. Cost and all. PLCs sell for around $100, $150. These are when you saw it's a Cortex M3 or something. These are pretty low end embedded devices. So the cost and all. Okay. So let's see where we are time wise. Yeah. Any other comments?
I have a same concern with the training data they use to train their neural network since they said they use the pre-processed signal trace, and I think this kind of data set based on my own experience is too like specific, and it will like make the model to have a very low variance, and sometimes if they have a larger like interference, then it may generate a lot of false positive. And I think for the questions you mentioned earlier that if there's like a different value in the control flow, I think if they train with maybe some general like signals, I mean, if they have a different set of signals generated from the batteries, then I think this won't be a problem. But
I think generally speaking, so there are a few issues firstly. So depending upon the processors, there are some processors where there isn't a whole lot of instruction to instruction power variation. Okay, so let me say add and multiply and all. A typical RISC processor, all instructions are single cycle, and they look pretty much all the same. Power profile is reasonably flat. The reason power profile varies is when something unusual happens, like going out to the memory or stuff like that. But on the other hand, complicated processors like Intel's one and all, because we have microcode there also as well, their instruction to instruction there can be variant, right? So that's one part. Different. The other part is for the same instruction, does the data value affect the power? Okay, and floating point, yes, because most floating point instructions are implemented separately in FPU, and sometimes the time they take depends upon the data value. But for your typical integer instructions, it's very unlikely that for complicated processors you're going to see anything. We did some work in my group with really tiny microcontrollers and with very so we were looking at power line, EMI. We could make some distinction on data values, like if you were moving one register to another and the register at a 0 versus some other pattern. We could make some distinctions there, but it's incredibly hard to do it. With EMI, I would be surprised you could ever do that. I mean, it's a very noisy signal. I think the weakness, the way I kind of see right now, is that they're not really doing a penetration test in the sense that how good is it, how reliably is it detecting the bad guy, what kind of compromises are you doing. I think they're kind of silent on that. Anyway, it's work by my friend collaborator, so I won't badmouth it too much. So, but it has been any other comments?
Like, how robust would it be to spoof signals?
Yeah, I mean, could the adversary compromise knowing that you are monitoring this way and hide? Well, so some of the attacks we're talking about are of that nature, right? Maybe don't change the control flow because control flow change are easily detectable, whereas value changes are not. So you can think of mounting attacks which maintain the same signature. It's again, security. Let's go back to the point I made earlier. You've got to think of security as a game, okay? And no other way. So adversary is not static, adversary is not stupid. And you would be surprised the extent to which adversary is intent on making good. So anyway, so let's reconvene on Thursday. I have office hours right now. So few things. So any of you who need hardware purchases, please come and meet me. And also any group which hasn't identified a project yet. Hold on. So you guys need to talk to me. So let's see. So on the order list thus far, let's see. There is ratio. Okay. There is the SDR, which was the time SDR. Yeah. So actually, that should have arrived. No, sorry, it's not. Okay, there's one SDR which should have arrived. And let's see, do you need anything? No, okay. Anyone?
So yeah, the contact was behind the scenes. So we're busy trying to work some hardware out there. Then we'll send the.
Okay. Okay. So basically, sounded like you need nuts or something.
We think we'll change over to a laptop platform under the recommendations.
Okay. Okay. Just let me know.
We just want to see
Okay. Okay. Yeah. So don't see anything, but just check.
If we figure out what we need, should we send it to you on the answer and email, or is there like a spreadsheet?
I didn't create the spreadsheet.
Okay.
Reminder on my previous email for the project.
Shit, I'm so sorry. Yeah.
Yeah, so I'll get back to you on Thursday regarding that. Or...
Yeah, or if you want to come now.
Okay, yeah.
Professor,
What are you doing?
with Leon and Insight.
Oh, okay.
The home network activity
Right.
detection.
So
I think we can use equipment.
if you need
similar
it, or just order through Faye and just okay, whatever you need.
Okay.
Okay. Just
okay,
CC me so that I can tell her the branch number.
Let me contact with Leon
Okay.
tonight. Yeah.